Hello, everyone. So this session, Agentic RAG meets a Neo4j multi-hop reasoning over scientific knowledge graphs by Annabelle Banchero and John Lilong. Over to you guys.
Thank you very much. We're very happy to be here today to talk about this very interesting project and how we combined multi-tool agents and graph knowledge-based information. Just one word about the company we work with. It's Equimetrics. We build solutions for different type of clients. We have different offices around the world, and we quite tech agnostic, and we do custom-based solutions. And we did this project with INRAE, which is the French National Institute on Agriculture and the Environment. And we especially did that project. No, can you go back?
Yeah, I'm sorry, I will have to.
We did this project with the Open Science.
Because otherwise it will change. Sorry.
Yeah. And the Open Science department is how to talk about the science that is being done at INRAE. INRAE has more than 2,100 researchers, lots of engineers and technicians as well, and they publish more than 5,000 publications per year with different other institutions, and they have projects that are financed by different financial institutions, and they usually need to find information within that huge database. And it's usually not just an answer to scientific questions, but it's more like what is the most known researcher in that topic, or what project have been funded by this fund, or how many publications did INRAE produce on that topic. So it's a bit more complex information. And they came to us asking, could we leverage new knowledge management technologies to improve the retrieval of these science-related questions, but not purely scientific? And to do so, we started by implementing a knowledge-based system, and we went for you can move to the next one. We moved to a graph knowledge-based. We used that to unify 3 different data formats. We had a lot of tabular data about the publications. We had who published it, when, in what journal, and all the information around the publications. We also had information about the funding, the project, the institutions, lots of different tables around all this. We also had unstructured text, the publications themselves, and we had a lexical tree of all the concept and sub-concepts that was all well organized into this lexical tree. And we combined all of those into one unified knowledge graph.
Here, a really important point was that for tabular data, it was really easy for us to find exactly the right combinations of relationships between entities. Usually, it's one of the most complicated steps of using a knowledge graph in an AI application is making the knowledge graph itself. Here, it was really fit for this use case. And for the unstructured text, same as we used scientific papers, it was very structured informations with like keywords usually at the same place and authors at the same place and so on. So it was really easy to navigate. And then for the lexical tree, it was to make a link between their way of interacting with the data and our knowledge graph that we made from that data, to use the same words and the same definitions that these very specific and technical people use. So here, this is the knowledge graph we made with about 10 different types of nodes centered around the publication node, with about 400,000 nodes in total and a little bit more than 1 million edges. We centered everything around publications to reflect the way we extracted the data from the different papers, and also because it made sense in this particular use case. So lots of different authors, and just to explain a little bit more, a few different nodes, keywords, where the keyword declarated by the authors when publishing their work. So it's written by them. And the concept and domain that you can see here in purple and green are from the tree that they had. We took every node of their tree that had different subdomains after it, and called it a domain. And then we took all the leaves of these tree-like structures with the definitions and called them concepts. The other ones are pretty self-explanatory. Software is the software used in the scientific publications. Dataset are the different data used in the scientific publication. Yeah. Then this is an example, an extract of the graph that we constructed with a publication in the journal it was published, with the this graph. We made an LLM agent with access to several tools, with a knowledge graph tool to interact directly with the knowledge graph, but also two other tools, and I will detail each one of them next, to find entry point into the graph, and then a fourth one, more complex, that we hard-coded with some rules to identify experts in the graph. That was one of the big use cases that they gave us, was to be able to identify expertise in different topics among all of their researchers, all of their university. So for the first tool, it was just a Cypher query tool. So we allowed the model to write directly on the graph, of course. And so here is one example, pretty complex, to really show how good LLMs can be with writing knowledge graphs. Here, for this particular example, we used a recent OpenAI model, but we coded the entire application with open source or open weights models. So it could also work with the last DeepSeek model or any Agentic capable model. So yeah, pretty straightforward. And then we were looking for ways to give IDs to the model to find better entry points into the graph based on the words and the semantic inside of the chunk we use to represent each publication, which was title, abstract, introduction, and conclusion, that we extracted from all of the publication we scrapped from the internet. And then we used an hybrid search pipeline that you can see here with the query. Then we represent the query with two different vectors. One semantic vector, so a classic embedding by a B encoder to represent really the meaning behind the different words of the query. And then in parallel, we create a sparse vector to represent which word are or are not contained in the query. So to be able to tell if specific words are in common between the query and the different documents. Those are very complementary because the first one is able to really have a feeling for the meaning behind the different words and synonyms and the negations and so on. And the second one is very important in this context because lots of words don't mean anything for B encoder. For example, names or very technical vocabulary are not present in the training data of the B encoder. So it's really important to have both. And then we used a step of re-ranking to merge efficiently those two and have really the most relevant publication. So this is another tool the LLM agent have access to find an entry point and usually to use the ideas it will get at the end of this line to write cipher code. And on the same ID, this is another tool written with Neo4j to find different concepts and keywords. So concepts are the vocabularies they usually use, and keywords are the declared keyword by each authors of their publications. And so this allows the model to find the same here entry point into the graph to really have a topic entry that will lead to several publications. So for example, climate change or things like that. For the keywords, we understand directly how it works. And for the concept, one thing maybe I was not clear about is we detected if the concept appeared in the chunks that we selected from the documents. So again, title, abstract, introduction, conclusion. And if so, we created the link, the edge, sorry, between the concept and the publication. The LLM agent has access to, which is more complex, more hard-coded based on rules we decided on with them to identify experts in their field. So it calls several times each of the other tools in code, in hard-coded program, and then give a consolidated score of the expertise of each researcher on a given topic. So here we will show you a few examples to really ponder how good this approach is compared to classical residual augmented generation.
Thank you very much.
And then we will show you a few concrete examples of demonstration.
Yeah, sometimes we're losing you. So yeah, so measuring performance of this kind of systems are pretty tricky because they don't do things the same way and they don't necessarily have the same results. So we try to give you some qualitative examples of the way a classic RAG would respond to some questions, an agentic RAG, and our agentic knowledge-based, graph knowledge-based RAG. Let's take one example. For example, this question: which research units publish the most on climate change, and which authors contribute most of these papers? So here we have two different questions within one. So it's a multi-hop, and definitely the classic RAG is just not able to answer the question at all. The classic RAG would be just based on the publications themselves. And its reply is to just ask for more information to the user. The Agentic RAG manages to extract a bit more context, but also admits that it completely lacks information to answer the questions. What our system does is that it would first extract the keywords and the concepts that are related to climate change. From these keywords and concept, it would extract the publications that are related to these, and then we'll research the research units and authors that are affiliated to these publications. And then it would rank all of these research units and authors by the number of publications. So it's able to do this multi-op, looking for information within the graph knowledge base through these different entry points, and it's able to answer this complex question. If we take another example.
Just to be extra clear with the different definitions, in our experimentation for classic RAG, we used an hard-coded pipeline that will just do one retrieval call based on the user query, and that's it. With the top 10, let's say, we use top 15 extract from the text of the knowledge base. Then for Agentic RAG, it's the same, but it's just the LLM that has access to the retrieval tool. And then for Agentic KG-based RAG, it's what I explained just before.
So if we take another example, what is the oldest publication available in your database? Here we just compare the Agentic RAG and our solution. The response that the Agentic RAG will give is basically, I can't pinpoint a single oldest record. It doesn't have that metadata information that would allow it to pinpoint that information. Whereas our solution is giving the answer that is legume nodules published on the 1st of January 2019. Because it is using the research graph and is able to then rank publications by date and then give the oldest publication that he has in this database. So this question, even if it's not a multi-hop and it's more simple than the previous example, an Agentic RAG is still not able to provide a correct answer on this. We have another example to give you. Is your current knowledge base? How many articles were published in 2022? Same idea. I think we can go a bit faster on this one. Another question would be that is a bit more complex. Who are the researchers in common between the two research units, Paris-Saclay and the L2A? Here, the Agentic RAG did not even understand what the L2A was and asked for more information from the user. And here, hybrid search is definitely not appropriate to answer this kind of questions. Our solution does gives the proper answer with the two researchers that are in common between the two research units. It is able to do multiple queries to gather the information and then to compare that information. And I think we can see more details in the next question, a bit how it works. Another complex question where we have what researchers published at least 4 papers in 2020, but had 0 publications in 2021, and then asked to rank them by number of publications in 2020. Again, the Agentic RAG is absolutely not able to answer this question. It completely struggles with negative queries. Finding what is not there is extremely difficult for the Agentic RAG, whereas our solution does that very well. It is able, using this multi-hop and using the knowledge graph, to extract all the information and then to rank this this information into the table that you can see here on the right.
Before showing
before
you
we have quite a few
demonstration.
questions, so I think it is interesting to leave some time for the questions in the end.
Okay.
Yeah.
Just so one thing before going to the demonstrations, it's really important for us, those few things, because for clients that we do RAG for, they don't understand exactly how RAG retrieval augmented generation works. So it's often counterintuitive to try to explain to them. It cannot know what it doesn't know, and to explain that we cannot have exhaustivity, we cannot count things in the knowledge base and so on. So it's really easier to use these types of agentic knowledge graph based RAG because it's much more intuitive to understand the limits of the agents.
Absolutely, and we are currently
so now
working
a few
on...
examples. Maybe we can show.
Jean, can you hear me? Yeah, 1 second. We are still working on formalizing a very good performance measurement framework for this, that we could quantify a bit better all of this. We have different dimensions, as Jean explained, the exhaustivity, for example, and all of that. If you have any suggestions, we'll be happy to look into what you could suggest. Demonstration now, Jean. Thank you. Did we lose Jean?
Yes, and that here, for example, so here we ask a question. Sorry, can you hear me?
Yes, I think you're back. Yeah, maybe start again the demonstration.
Okay. Wow, there is a delay then. I'm really sorry. Okay, so this is a demonstration. I don't know if you heard what I explained, so I will do it again. It will query iteratively and investigate to find the different hopes necessary to go to the final answer and to gather informations on the topic. And then it will explain everything it found in a clear way for the user. Maybe we have time for one other video before going to the questions.
Yeah, yes, because we still can't completely hear you. So yeah, let's give another example. I think it's a good idea.
Do you want to do the voiceover? I'm sorry if you can't hear me.
Yeah, so this is also to show you the type of interface that we've developed alongside the solution. On the left, you have the interaction interface user, where you have the system giving its thoughts and explaining each step what it's doing. And on the right, you have the details of different queries. And so you have tables, you have graphs, you have the extract of every single steps. So you can check the information that it's giving. So here we're asking the top 5 experts on climate change, and you can see on the left that it's thinking about it, first of all, then it's doing a search experts using the expert tool that the system has access to. And I can't see your screen anymore, Jean. But I think it's okay. Let's try to answer some of the questions from. Oh, it's back. Okay, so yes, so you have the final answer on the left, but you can see all of the different mid answer on the right. Jean, do you have a place where you can show that we can show the graph extract as well? Yes, so here is the part of a graph that has been extracted in one of the queries, and we can show this in the interface as well. Okay, thank you very much, Jean. We have 4 minutes. We have a few questions. If I go back to the beginning, what was there?
I can't really hear you most of the time. I'm really sorry about
okay. So what was there a direct link between papers, tabular data, and the tree of concept, or did you have to make the mapping yourself? We did the mapping ourselves between the tree of concept and the keywords that were in the papers. So that has to be a little matching there. Yeah. Another questions. There's a lot about hearing problems. Another question: how did you build the text to cipher model? You give context from the knowledge graph to the LLM. So the text to cipher. So it's mostly from the LLM that does the cipher query.
Yes. So
yeah. Go ahead.
Yeah, no, sorry. There is a big delay, I think. That we wrote the schema of the knowledge graph in the system prompt of the LLM agent, and then we gave a few short examples of different queries and how we were expecting the model to react. And this was it, and it worked like a charm.
Another question: any idea of time performances for this model?
I'm not sure I understand, but if the question is
the time it takes,
the time it takes to answer a question, it's the tool calls are instantaneous, so it just depends on the speed of the LLM itself. It's really quick.
It takes a couple of seconds, though, no? It's not instant.
It does. I mean, the tool call themselves are not what is driving the performance. It's really the speed of the LLM and So it depends on the API you're using or the framework, I guess, if it's local.
Is there a way to access these slides deck later? I think we have no problem sharing it. Jean is projecting here the QR code for the archive paper, and this was presented at ECAI last week, 10 days ago in Bologna as a demo track. But we have no problem sharing the slides as well. Can you explain in more details how you made the semantic search agent-based?
So I think you're talking about the hybrid search. So it was, to go back on the slide, it was just oh no, you mean semantic search, just this part of the pipeline.
Yeah.
It's a B encoder. So we created the different chunks for all the publication, then created embeddings for each one of them. And then we used QDrent to query easily with a cousin similarity of the vector we created based on the query the LLM wanted to search. And then we just compare all of the vectors to find the top K vectors that are the closest to the query.
I can see that we have 17
this node,
seconds.
Just this node is really, sorry.
No, go ahead. No, go ahead. It's better that you finish the answer.
No, but there is too much delay.
we will try to answer those questions, the additional questions online. Thank you very much for your attention.
Thank you.